Hello, in this presentation, I'd be making a rather modest assumption. The assumption would be that most and not all of my vehicles are semi-autonomous in nature. Semi-autonomous means two things. Firstly, if there is a complex road network like this containing multiple roads, and any one of these roads contains multiple lanes which may be occupied by multiple vehicles, it means first that most of the vehicles I can track where they are, how are they moving, with what speed are they moving, in which lane and road they are moving, and secondly, I can give them some kind of driving instructions, I can give them some kind of information, or I can tell them what and what not to do. So with most of the vehicles, if I can do these things, that is my entire transportation system is largely semi-autonomous in nature, then what magic can I produce? And the very thought that I can take some kind of information and give some kind of instruction, it opens in a pool of thoughts that you can yourself sit and visualize that what all possibilities can be introduced into the transportation system, into the traffic system, if this basic assumption is made. Now, the obvious thing that would happen is that what we've got as the static traffic rules, they would become more dynamic, which will now become the dynamic traffic rules, where we'll see the rules themselves change with time. The system itself decides which rules are good for the system as per the current state, which will be good for in the future. So all the concepts that we follow today, they become more dynamic in nature, they become more efficient, they become more collaborative, where different traffic entities are trying to help each other out. So we'll be seeing at all these kinds of imaginary magical things that can happen in the transportation system. And of course, when we need some kind of magic to happen, we need a very challenging kind of problem for that to happen. So this would be the central theme of the entire presentation, and the theme is that the vehicles are very diverse in nature. So we've got slow moving vehicles, we've got fast moving vehicles, we've got very fast moving vehicles. In fact, the original motivation behind this work was to create some kind of traffic simulation system, a big broad traffic simulation system for an unorganized or chaotic traffic, for which both the sizes and the speeds they vary. We've in this presentation, of course, I'll be presenting a very basic miniature version of it, where the traffic is entirely organized into lanes. It's not chaotic, it's not disorganized. But we will see that even in such kind of organized traffic, what can diversity do, and how can these magical things be made to still be efficient, still be good in such kind of diverse speed environment. So from now on, the next slide onwards, what I'll be doing is that I'll be taking each and every traffic entities that you see in the transportation system, and we'll see that with such a kind of assumption, what can we do with such kind of speed diversities, what can we do to make them still better. Now, the first of the very important things that comes in, so many times it happens that in a traffic crossing like this, where there's a traffic crossing out here for each of these sites, there are huge pools of vehicles at each one of these three sites. I'll draw better graphics out here. So there are huge pools of vehicles at each of these three sites, and there are very few vehicles out here. The traffic light turns green, that means all these vehicles can simply go. Within say 10 or 20 seconds, this traffic gets clear. But all these vehicles have still to wait, because there was a 2-minute time for this road, and you really need to wait for the rest of the 1.5 minute, even though there is nothing moving. And that's simply because the traffic lights are blind. They do not see traffic is there or traffic is not there. They have been just instructed 2 minutes for this side, 2 minutes for this side, 2 minutes for this side, and 2 minutes for this side, and that's very annoying in such kind of traffic. So as I said, all the vehicles can be tracked. It naturally means something magical happens right here only with this assumption that after 30 seconds, after 20 seconds, when traffic from this side clears, this side can be said now you can move. The traffic light can turn green for vehicles from this side. Because the vehicles are tracked, I can come to know when this road gets clear and traffic can now start moving from a different side. So that's of course the very basic kind of advantage that this system has right from the very word assumption. In general, what we have, there will be vehicles at each one of these sites. What we want is that we want to minimize the waiting time of all the vehicles, of course. And the way we do that is we say every time the traffic light will go green, every time a traffic light will change for the vehicle which is the most waiting vehicle in the lot. And that's very something very natural for the humans. We say that if there is a queue for any kind of job, say in for any kind of reservation or train reservation to happen, so the person who has waited the maximum in the queue, who of course is the person who was the first to enter the queue, will have his job processed. And similarly here, the most waiting vehicle will have a chance to go through this crossing region. And of course, in such a scenario, when what we have is that suppose the most waiting vehicle was from this side, so this line turned greens, which means this entire vehicle pack is allowed to move, and not just the most waiting vehicle. The entire pack is allowed to move, and after this pack gets clear, this road gets clear, then we can allow either this pack or this pack or this pack, depending on whichever pack has the largest waiting vehicle. So whenever there is no vehicle in the current side, the traffic light will allow traffic to move from some other pack. And of course we know that every traffic light has to be thresholded by time, and here because the vehicles are being monitored, I can also threshold them by the number of vehicles passing. And the advantage of that is very clear. Suppose there was a big pile of vehicles over here, and these vehicles were very densely occupied, very lightly occupied. Now this might take in 4 minutes, but this poor guy over here should not wait for 4 minutes for the entire pack to clear. So I threshold it by time and I threshold it by the number of vehicles, and I've got uh, another heuristic that I placed in over here, which again happened by realizing how do jobs get processed in a human society, or what is the advantage that I can add if the vehicles are being tracked. Now what we have done in this implementation is, suppose there was a big pack over here, or let's say there was a moderate pack over here, the traffic light turned green to allow this pack, and there were some vehicles out here, and out here. Now if a new vehicle comes in while this pack of vehicle is moving, it would be said that you cannot move. It would be said that you have to wait for a crossing, because even if this vehicle moves, it would not be unjust for this vehicle, and this vehicle. We want to minimize the most waiting vehicle. We want to minimize the waiting time, which was by doing some kind of first come first serve or a queue based approach, where we said the most waiting vehicle would move as compared to this vehicle. This vehicle is more waiting, and hence this should have a priority over this. So every vehicle has to wait for at least one crossing when traffic light change. That seems like a reasonable strategy to implement even when thought manually. Every vehicle has to change for at least one traffic light change Of course, which is not the scenario if there were no vehicles at each of these sides. So this pack of vehicle would move even if a new vehicle comes in. There are no vehicles at the other side, so it would be allowed to move. So these are simple heuristics that we have placed, and this is a graphical representation of what actually would happen. The vehicles are numbered in their order of appearance. So first this vehicle came in the scenario, then this vehicle came in, and so on. This pack of vehicle is allowed to move because the most waiting vehicle was here. Then this would be the scenario. In the vehicles left over, this obviously came in number 1. Then I've got the least number 4, which means the second most waiting was here, and then third most waiting was vehicle was here. Then this pack would be allowed to move, and then this pack would be allowed to move. Of course, as new vehicles come in, they would be handled accordingly. So we simulate this system, and while we simulate this system, we keep two other systems intact. The first is exactly the same system as here, except for one thing, that it first allows traffic from this side, it then allows traffic from this side. So it's a cyclic traffic light change. The traffic light is thresholded by the number of vehicles, by the time, as well as the time, as well as whenever a vehicle pack from one side clears, automatically the traffic lights change. And this is the current system where it will say for a threshold amount of time, say t seconds, it will allow traffic from this side, then another t seconds from this side, another t seconds from this side, and another t seconds from this side. When we simulate, this is what we observe. This was the proposed system. This was the system that we were proposing, and for moderate scenario, it can be seen that it performed better. And it's a stochastic system, so such small differences, they do not actually matter. This system obviously had the problem that the traffic from one side got cleared, and the traffic lights were still waiting. Now, what happens at a very high number of vehicles, or what happens at very high traffic density? We've got a scenario like this, where there are huge pools of vehicles out at each one of these sides. Suppose my proposed system allows traffic from this side, and most of these pool of vehicles get clear. The second most waiting vehicle would be here, the third would be here, and this is the order in which the traffic light would change. So the pattern in which it allows traffic light to change once, the same pattern would be followed again and again. So basically that's why it will behave more like it will behave exactly similar to a system with cyclic changes in the traffic lights, except for the cyclic, it may be acyclic or it may be some other order. And in order to highlight the differences more, we said that earlier we were generating the same kind of traffic at all sides. Now we say that no traffic gets generated here. Traffic is only generated at these three sides, which means this poor little system over here, that was a cyclic change with definite time, t seconds here, t seconds here, t seconds here, and t seconds here. This system obviously faces a problem. It will wait for t seconds for this side, and no vehicle is clearly coming from this side, so that time is simply wasted away. Whereas the proposed system again marginally performs better for moderate to high traffic densities. This is when we say that the traffic was time thresholded. So in the system with cyclic light changes, what we said, t seconds here, t seconds here, t seconds here, and t seconds here, the same parameter t we are varying. And for the other, it says that after t second, a traffic light change has to happen. So again, the definite time change, this system is clearly the worst, whereas there is no difference between the proposed system and the system with cyclic time of change. And here, as we see, increasing this time does not matter anymore. If I still further increase this time, it will still be a straight line like this, and the reason for that is, suppose there were 30 vehicles here, there were 30 vehicles here, there were 30 vehicles here, and there were 30 vehicles here, and say I said traffic will change at 2 minutes. Now these 30 vehicles need only say 1 minute, after which the 31st vehicle enters over here. My traffic light should ideally change after 2 minutes. That means 31st vehicle has entire 1 minute to travel, but I placed a heuristic, as I said in the earlier slides, that every vehicle has to wait for the traffic light change. So this vehicle will not be allowed to move. After 1 minute, a traffic light change will happen. That means this golden number of 2 minutes was not at all used. So that's why you see a straight line out over here. In high traffic density, which was the case with my previous slide, in high traffic density, as I said, it does not matter much whether I'm doing a cyclic change between traffic light where traffic moves from here, then from here, then from here, and then from here, or I'm saying that the most waiting vehicle is preferred. It makes that the most waiting vehicle gets preferred. All this system has no major differences because this system will degenerate into this system where there will be some order between the traffic light operations. So I say that I experiment only for light traffic scenario where it can be clearly seen this traffic is much better than this, or the proposed system is much better than the system with cyclic changes. Now, a central issue in this entire mechanism in which traffic light should be operated. Now, I give two very contradictory and very extreme scenarios. I say one is the system in which there was some traffic pack of traffics over here. I'll say which is the most waiting vehicle. It may be this vehicle out over here. I say now you go. I'll say now which is the most waiting vehicle, maybe this vehicle, okay, now you go. The third most waiting vehicle, it may be this vehicle here, now you go. Now what's happening? First this vehicle goes, the entire time that this vehicle takes to start, to enter into this region, to clear this region and to exit, no other vehicle is moving. When this vehicle does the same thing, no other vehicle is moving. So there's a lot of time wasted when we change traffic lights. Every change in traffic lights means a lot of lateral time is wasted out, and it is largest for this system. The completely contradictory thing would be that if there is a vehicle over here, there's a huge pack of vehicles over here, and over here. Now it should not be that this person has to wait for this entire pool to clear, then this entire pool to clear, then this entire pool to clear, only because they were with vehicles that were entered before. Each of these side was with at least one vehicle that entered before. It should not be that this person should wait for all of these. So this is one extreme where I make two frequent light changes, and this is another extreme where I make two infrequent light changes. What the simulation suggested that this is better, it suggested these as the best, because I was averaging out the waiting time. I wasn't saying what is the maximum that the person has to wait. If that had been the case, then if this would have been by simulations come out to be the worst. So these are two very broad decisions that one has to make while designing a traffic light and designing the mechanism by which the traffic lights operate. And I'll move into the second concept that we deal out over here. The second concept is of speed lane, and as we all know that in cities there is a lane which says that only higher vehicles can come in this lane, and all the other vehicles or speed with lower speeds, vehicles with lower speed will drive at this lane, and therefore the traffic is very fast in this lane, and there are some slow moving vehicle out at this lane. That's how traffic is organized. In general, what happens that the government fixes and say 40 miles per hour for this and 30 miles per hour for this, or 20 miles per hour for this. This is the speed that is limited. Now in general, what we see that traffic is known, what kind of traffic is known, the density is known, so government can fix in these magic numbers. While what is there in our problem that we have taken, the vehicles may vary from say 5 miles per hour to their preferred speed will be 65 miles per hour. So that is one issue that we need to deal with. The second issue that we deal with, that maybe vehicles in the range of 5 to 30 miles per hour is completely absent in the road at some time of some time span, and maybe vehicles from 40 to 65 are completely absent at some other time. So depending upon time, depending upon scenario, depending upon the time of the day, depending upon the road, depending upon each one of these, the road may be diversely occupied by very different kind of vehicles. So that automatically says that these speed limits need to be dynamic. They need to change as the traffic inside it is changing, and secondly, they need to be robust to this very high traffic speeds and not such a low difference in traffic speeds. Now, in what we do out here, we say that the minimum speed limit is fixed. So if I say the minimum speed limit is V1, only vehicles whose preferred driving speed is V1 or more will basically get a chance to drive in this speed lane. And similarly, if I say that the speed limit is V2, only vehicles with speed V2 or more will get a chance to drive in this speed lane. So the minimum has been fixed, which says you cannot drive it at a high speed lane with anything less than 40. You have to be 40 or more. That's what this concept basically says. Now again, we need to consider the fact that in this kind of modeling, the vehicles have very diverse speeds. So if I fix the speed limit of this to be 30 miles per hour, the low, that means 30, 40, 50, 60 miles per hour, these vehicles would be traveling here. So let us say I'm traveling at 40, and let us say this vehicle is traveling at speed limit of 30, which is valid, and this is the lower speed, this is the higher speed lane, and this is the lower speed lane. The lower speed lane is currently empty. Now ideally what would happen is that this vehicle will start following this vehicle and start driving as 30, because this is high and this is low. What I say that a higher speed limit can always enter a lower speed limit, and if this is allowed, we can say that the 40 will go here, it will come here, and it can again overtake the vehicle with a speed limit of 30. So a higher speed vehicle can jump into the lower speed lane, and that will normally result in some kind of overtaking behavior, as we saw out here. Now the basic concept that we use is in the entire we've got some kind of road like this as shown in this diagram, and in this road we have got some basic kind of, every vehicle is traveling at some different speed. These may be vehicles with painfully low speed, these may be very high speed. So in this entire road, I see two vehicles. I see the lowest speed and I see the highest speed. So out here I have got that this was the vehicle which had the highest speed and this was the vehicle which had the lowest speed. I've noted down these two vehicles, and I've simply assumed that all the vehicles in between have got some kind of speed, uniform speed variation in the speed band. So if this is my speed axis, my lowest speed vehicle is found here, my highest speed vehicle is found here, and the other vehicles are found in this uniform speed band. I cut these speed band into slices. So there were 1, 2, 3, 4 lanes here. So I cut them down into 4 slices. And as you can see, the slices have different speed limits. The slices have different widths. And widths here are basically speed bands. So the slices have different speed bands. And I basically say the vehicles out in this lane, any vehicles out in this lane, which means all these vehicles will be the vehicles which belong to this speed band. They'll have a lower speed of this and they'll have a higher speed of this. Of course, they can have speeds higher than this if possible, but they cannot have speeds lower than this. All vehicles in this lane will have speed within this band, and of course they cannot have speed lower than this. They may have speed higher than this, and they may not have preferred speed lower than this. The operating speed can be lower if the road is really congested. If it's not possible to drive at this speed, there's naturally nothing that they can do, and so forth. So my distribution is weighted, where weight denote the different widths. And out, when we see simulate this kind of system, I take in two lanes, as was the case below, where there will be a higher lane and there will be a lower lane. I compare it with the system where there's no speed zones as such, so any vehicle can drive anywhere. Now this should of course be a straight line. It's a stochastic system, so you see small variations out here. In principle, it is a straight line, and I see that when I implement such kind of speed where my entire speed loan is divided into two regions. So this is the speed band, this is the speed band here. It is divided into two regions weighted by W. W equals to 1 naturally means that the speed range of the first band is from the lowest to the highest, and naturally this is the speed band of the higher speed lane, and for the lower speed lane, of course, any vehicle can drive on this speed lane, which means both the lanes can be occupied by any vehicle, which means that both these systems are equivalent, and obviously they perform equivalent in this region. So I can naturally see that my system is performing better than a system with no speed lane. If I keep my W to be 0, that means there is the higher speed lane which is so privileged that only one or two vehicles have got speed higher enough for that. So the entire time only one or two vehicles drive here, and there are too many vehicles out over here, which naturally means effectively I have got only one speed lane operational if you forget these one or two vehicles in the entire simulation study, which of course says it's better. That's why it's dip. It gives the best performance, and that it starts degenerating into a system with no speed lanes. And this is another study that I do. This study was for a densely occupied scenario, so there are too many vehicles out over here. Now when we repeat the same study for a lightly occupied scenario, an interesting thing happens. And that interesting thing is that my system, or the system with speed lane, is performing worse than the system without speed lane. And what's basically happening, if I've got two speed lane, where this is the highest speed lane and this is the lower speed lane, I see a vehicle like this. Suppose the limit of this speed lane was 30, and this was driving at a speed this vehicle was driving at a speed of 30, and I have got this vehicle which is driving at a speed of 40. I'll have to consider the converse. I'll draw it again. There are two speed lanes, which is a higher speed lane and a lower speed lane. The speed limit of this is 30. This is a vehicle which is traveling very slowly at 10 miles per hour. This is a vehicle which is driving faster, 20 miles per hour. And say there is a vehicle out here way back which is traveling at 40 miles per hour. Now what can happen if I maintain speed lane? This vehicle would follow this vehicle at 20 miles per hour, and this will travel at 40 miles per hour. It looks good. If I do not, and this is a lightly packed scenario, if I do not implement speed lane, what will happen? This 20 miles per hour will go here. It will change its speed lane within a very small time. It will cross this vehicle with speed of 10. It will overtake and it will start driving ahead. Overtake is possible. So it's a bad idea to implement speed lanes when your traffic is really lightly occupied, and that's what happens, that in roads which have got very light traffic density, we never have any kind of marking. Anybody drives anywhere they want. Of course, this is overtaking from the wrong side, which is not very common, but then it's very safe when it comes to driving in a lane oriented structure. And such kind of things you will never see in a very American or a British kind of traffic, because the vehicles are uniformly speed. They are either high driving vehicles or low driving vehicles. Such kind of scenario can only happen when vehicles are very, very diverse, which was in our scenario. I had 10, I had 20, I had 30, I had 40. In such kind of diverse scenario is where this fact would hold true, that implementation of speed lane for lightly occupied scenario is a bad thing to do. Now, one thing I said that roads at different time may be occupied by different kinds of vehicles. Not all, not sometimes they may be only high speed vehicles. Sometimes they may be only low speed vehicles. Important claim that I made was that the algorithm can adapt. If it sees only high speed vehicle, it can say that okay, very high here and reasonably high here. If it's speed high to low vehicles, it can say high here, low here. So how do we test this adaptability? We say that we will compare with a system which says high, low, and the speed limit of this is high plus low by 2. Or if I say the high is 0 and the low is 1, then the speed limit of this is 0.5. So this is my system which does not change. If my traffic dynamics, my traffic inside the this system consists of only high speed vehicles, it will still say that speed limit is this. If it consists of only low speed vehicles, it will still say it consists of the speed limit is this. And my second is the proposed system, which it can be seen it performs better. And what we are doing is that my simulation tool, it said that there's a lower bound in which the speeds are generated and there's an upper bound in which the speeds are generated. I first fiddled up with the lower bound. So if I make this lower bound very close to the upper bound, then there's no diversity. If I make this upper bound very close to this lower bound, then there is no diversity. In this experiment, what I'm doing is that I am changing the upper bound. So I'm making the upper bound travel from regions of from the lower bound, which is what happens here. The upper bound and the lower bound are same. So there is no diversity, to here, which means the upper bound and the lower bound are way apart. That means there's a lot of diversity, and it can be easily seen that my system performs better to a system to this kind of system with a static definition of a speed lane. And the reason why they perform similar at extremes, at this extreme I had a lower bound and I had this as an upper bound, and this was what was my speed limit, and that is exactly what my static system was doing, where the lower bound was the lowest possible, upper bound was upper most possible, and that's what it said. Here what happens at this region, why do they perform the same? That I had no diversity in traffic. That means the traffic was very similar. So what this system would do is that the same vehicles it would travel with at both the speed lanes. There are only vehicles with similar speed, and in this system what would happen is that if this speed is very low, all vehicles would basically follow each other. And of course it does not make a difference. The vehicles are uni-speeded. They all can follow each other without anyone losing any time. And this was the other case in which earlier I moved the upper bound, now I moved the lower bound, which means there was a lower bound here, there was an upper bound here. I'm sliding this lower bound from very low value to a very high value. So here the two systems would be the same. They would be vehicles of the same speed, and here the vehicles would vary a lot in their speed. The upper bound and low bound would be very different, and it can be easily seen our system performs better. The other concept is one of the major concepts, that is route planning. So when I have got a very complex kind of city kind of map over here, I'll draw a vague road network like this, where all these are nothing but roads. There are too many roads out here. Now one thing that we always need to consider is that, suppose I have got two options. So in this map I mined out two options. One was a very straight option like this, and the other was this kind of option which had all these turns. It looks this would be better than this. However, there might be too many vehicles out over here, and this might be very less occupied. So it's always a choice between selecting a shorter route and a more congested route. A shorter route is better and a less congested route is better. You need to balance between the two. And how do we balance between the two? We say all between any two objective. We say it's simply the first objective penalty times the second objective, where this is my algorithm parameter that I'll be trying to optimize. And important factors, of course, that the traffic density is only known. Suppose this is our source, this is where we are currently located as. The traffic density is known only for these roads, because when I travel at these roads, the current traffic density will be what I expect. For these roads, I'll come at these roads, say a minute after, 2 minutes after, traffic density will not change much. But I'll come at these roads, let's say 15 minutes after from the current time, so I cannot rely on the current traffic density. So for far off roads, in place of using the current traffic density, I'll basically use the historic information and I'll extract out what traffic density was previously in similar days available, and I'll expect the same kind of traffic density to be available. So I'm trying to predict the traffic density when I come out at these roads, which are the roads very far off. And at every road, if I know the traffic density that I'll expect, then I can use any simple graph search methodology to find out the way. Now when I solve the problem in this kind of manner, that I know that my traffic density is a dynamic element, it will keep on changing. Now when something keeps on changing, my best route by definition will keep on changing. When the best route by definition will keep on changing, I basically need to continuously replan. Now in road, what is true is, suppose that I'm traveling on this road, I cannot and I later find out that I have started from here to travel to the destination like this, and now after coming here I realize that this road was actually better. Now I cannot take a U-turn and go back, I'll have to travel in front. So basically I replan the at the maximum, and that means that I replan when I reach here, and when I reach here is when I come to the next crossing. When I come to the next crossing, I simply replan. I say that as per the current traffic density, which is both the current as well as the predicted, which route is the best. So that's what basically I'm doing. The traffic density was a dynamic element, so I need to replan, and I need to replan at every crossing. Now for simulations, I generate a nice scenario like this. This is what is the shortest path route from the goal to source to the goal. But then, as we see, along with time, this would get very congested. There will be long queues out in this, which is when this road will come to the rescue. Many vehicles will go here, a smaller number of vehicles will go here. But if I generate too many vehicles out here to go to here, soon this vehicle will also start getting congested, and then this vehicle would be a preferable choice. Maximum vehicles would go from here, some would go from here, and few would go from here. And of course, even when this gets congested, then there is no kind of option available. And I simulate this scenario. What I see for lower penalty, alpha is basically which was called the penalty previously. My proposed system performs better for most of the moderate values, and if I keep alpha as 0, basically it is my length plus 0 times or plus penalty times my traffic density, which means I'm only trying to minimize length. And if I'm only trying to minimize length, there is no difference between the proposed algorithm and an algorithm which only minimizes length. Now again, this should be a straight line because the system is stochastic. You see some flips out over here. Now what happens at this region when I increase alpha too much, or when I increase penalty too much, it becomes length plus a very large number times traffic density, which means effectively this term is close to 0 and it's only traffic density that matters. And what that means in the previous scenario, it will only try to minimize the expected traffic density that the vehicle expects. So the first vehicle will go out here, the second vehicle knows there's a vehicle out here, so it will go out here, minimizing traffic density. Third vehicle will go out here, the fourth vehicle will go out here because the traffic density is equal. So traffic would happen such that the traffic density is equal on all three roads at all the same time, which is clearly bad. This vehicle should have more traffic. It's more short in length, and as we see, the performance is bad. If we increase alpha further, it's only minimizing the traffic density for this kind of objective function. No matter what penalty you keep, it's only trying to minimize density, so it will be a straight line ahead. And one of the last systems, which is of course the most simple of all. Now many times what happens is, suppose there is a concert in some kind of city which needs to take place here. What happens is that this road becomes very important. It will obviously be congested, so only VIPs can enter from this road. The general public is told you use this road, or maybe you use this road to come, which are long. As a result, what happens, this road is never congested because only few VIPs can enter through this road, while these roads are always congested. An important question out here, if it's an important concert, or let's say the VIPs are very important, really very important, then this kind of strategy is good. But in general, it is a valid question. Can we take some imported people from here, or people who are using general roads, and inject them into here? What will happen if we do that? The general answer is simple, that there are more VIPs out here, so there will be some congestion out over here. But we need to study that from a simulation perspective, that what happens if we keep on increasing the VIPs out here. In a more general terminologies, in a road network graph, suppose we know that this road is very important, it connects to very important places. Can I book this road based on some money, or based on some social importance, or based on something? Can I book this road, and only people who have booked this road will be able to use it? That's what the general concept is there. And similarly, we've got something that the roads have lanes. So let's say there were 3 lanes out over here. Now can I book this lane for some money or for something? And that's what basically happens at any Olympic games or any other national games, that a lane is made Olympic vehicles only, and only those vehicles can come which are normally underutilized. So can some vehicles be injected into these lanes? Can I increase the booking? We need to study them from an simulation point of view. We need to study them from a simulation perspective and analyze the kind of impact that they produce. A good example of this is currently what happens if there's a police or there's a fire brigade. There is a flashing light that it has, there's a siren that it has, and whenever people hear the siren, they move from this lane to other lanes here or here. When I say that I can track each vehicles well in advance, I can communicate to all the vehicles, I can give them some driving instruction automatically. That what it means is that whenever the emergency vehicle would be close by, so let's say it's about to enter into this region, it can automatically book this road for itself and make all the other vehicles unbooked. And when the other vehicles are unbooked, they'll immediately have to change in their lanes because they do not enjoy that resource. So while the emergency vehicle was here, which is long way from the actual road, the other vehicles have simply moved away. So what this emergency vehicle sees, it's always a clear road. Unlike here where it has to wait for vehicles to clear off. So that's a very practical example of how this can also be used. And to test, of course, first the road bookings, we said this is the road only for VIPs, and this is the road for the general public, which is long. Naturally, people want to use this road, or also, although they are not allowed. We need to analyze how much percentage of traffic should be booked, or how much percentage of the total number of vehicles should be booked. If we book more vehicles, clearly now VIPs do not enjoy the liberty. The performance is clearly dropping for the VIPs. Now it's made on a very broad, the scale is actually very broad. it connects a very short route and a very long route. So if we see a magnified view of this, if we magnify this, what we'll basically see is that as we increase the number of vehicles, very soon the performance drops to very bad. That's what's happening out here. Very soon the performance is dropping to from very good to very bad. That means the VIPs are basically facing problem, and of course the VIPs also have speed differences from very high speed to very low speed. The speed is rapidly dropping until it comes to a scenario where the performance is so low that booking has no incentive. This is the what would have been the scenario if everyone would have moved through this load, and basically this load would not have been utilized at all. Everyone would have moved from here, and that's what we actually expected. That's why the number of, for any such events, the number of VIPs are kept to very very small. And if I inject out people from here to here, if I inject out vehicles from here, naturally the traffic density here there would drop. Less and less vehicles would use this road, and if less and less vehicles use that road, what will obviously happen is that this traffic will sharply fall down. Not it will gradually fall down, and this of course is a region where no vehicles are booked. No vehicles booked means they all use the VIP. They all use the alternative route. There is no VIP. There is a route which is booked for the VIP only, and nobody uses that. They all use the long route, and it naturally shows the worst performance. And exactly the same is the observation with lane booking, except for now that you see that there's only one scale. They were not two scale, and that's because earlier there was a big road. The time will be of a very different order, and a short road, and the time will be of a very different order. So the time will be very high over here, and time would be very low over here. While when I have different lanes, these two times are of the same order. And again here we see that if we book in more vehicles, the VIPs are at a very bad loss. Very soon the performance of the VIP lanes deteriorates, and the converse is also happening out over here. And so this is how we basically conclude. We are of course proposing a kind of simulation framework, a kind of transportation architecture where there are too many elements involved. So first of all, there would be a central system which tracks all the vehicles, which is like a central store of all the information that you need. I've already discussed the lane booking, the road booking, how to decide the speed lane between lanes, how to decide the vehicle routing algorithm. This is all that we have discussed. Each one of these uses some or the other information from the central information system to work. Each one of these has some kind of different information from the central information system, and each of these has some kind of different output that it produces. And based on all this, the vehicle is planned, as in which route it should select, which is from here, and which lane it should use from here. And low level control signals are used to physically navigate that vehicle. Either if it's a human will do that. If it's an autonomous vehicle will do that, which again gets monitored, and the information gets updated to the central information system. And to initiate, we'll of course need some kind of maps and all these kinds of things, as well as some human can directly inject in something out over here. The transportation authority can inject in something out over here. So that's what probably a futuristic transportation system would look like. In our case, specifically working with a very diverse kind of vehicle scenario, where the vehicles show a very great deal of diversity in their speeds, which changes all the rules of the game that we currently see and follow. And that will be all for the presentation. Thank you.